Welcome to the second part. Now I'll be discussing some basic properties about isoperimetric profiles. So in a few words, an isoperimetric profile, what it's doing is trying to answer simultaneously for any given volume, what is the optimal perimeter needed in order to bound such volume. So formally, if we have M to be some Riemannian manifold, we can define a real value function going from non-negative real values. That's the following. For any V, we're going to take the infimum of the perimeter of any domain U, so that U is going to be some subset of M with compact closure that has total volume equal to V. This is a fairly sort of like simple definition. As a quick example, well, if we take M to be R2 with a flat metric, there we know that the perimeters, the isoperimetric problem is solved by the circle. And because of the relation of, in this case, well, area and perimeter of the circle, then we have the isoperimetric profile should be 2 times the square root of pi times V. Okay. So these functions are interesting because in the way how they relate to constant mean curvature surfaces as follows. So I'm going to list 2 facts. The first one is that if I have a U that is realizing the isoperimetric profile for a given V, then the boundary of U is has to be a surface so that its mean curvature is going to be constant. And this is usually how we refer as sigma as a constant mean curvature surface, usually say briefly as CMC. Well, 2 is that essentially the derivative of the profile is given by the mean curvature of sigma. Well, in this case, and this is something that maybe it should be apparent in the way that the definition has been stated, that this doesn't have to be differentiable always, but it has a derivative at most points and at least in the left and right sense. And then what it does is that, well, it satisfies these inequalities between the derivative from the right and the derivative from the left. Which of course, if the profile will be differentiable at V, then all that this is implying is that the derivative is exactly H. So we just have to gradient this like weaker statement because we don't have enough information about the differentiability of the profile. Similarly, we have this inequality for the second derivative of the profile. Basically, it satisfies the differential inequality, where here we're integrating the Ricci tensor along the normal of the surface plus the norm of the second fundamental form. But then again, because our function is not going to be in general second differentiable, we're going to say that this equation is satisfied as a barrier. Where here I have, I'll remind you that I will say that the function has second derivative less than or equal than h at the point x0, where f is not necessarily smooth, if I have a smooth function g so that they coincide at the point f is lying below g, and the second derivative of g is the one that is bounded by h. So f here is allowed to have let's say not a smooth point, but as long as I have this sort of like pseudo tangent here, then I can talk about this type of inequalities holding. Okay, so we're interested in this functional, and particularly the way we're going to be interested in studying it is trying to prove comparison results for different Riemannian manifolds. So a quick example of such a result is the following. So there is a theorem due to Levi and Gromov that says that if your if the reach of your manifold is bounded below by n, then the profile of your manifold is greater than or equal than the profile of Sn, where Sn is the round metric in the n-dimensional sphere. Here, a quick observation is like it's not technically the profile in the sense we have defined, but it's rather the volume of the region divided by the total volume of M, because in this particular case, we know that because of this bound, we know that M has to be compact. And similarly, we have a similar rescaling for area. So in a nutshell, what we want to do is we want to restrict for a certain type of Riemannian manifolds, then we want to compare profiles between a generic manifold and what manifold that we're going to be calling as the moment. Okay. So what is going to be a very useful functional for us in order to study and describe these isoperimetric profiles is going to be the Hawking mass. So this was described by Hawking around 72, and it's basically described as follows: is that if we have a two-dimensional sphere in a three-dimensional manifold, then we define this mass as the square root of the area of the surface divided by 16 pi times 1 minus 1 over 16 pi, the integral of the mean curvature square per unit area. So this is the original formula. And here I'm adjuncting a -4, and reason being that this formula is usually the formula used for flat manifolds or asymptotically flat manifolds, and we're interested in hyperbolic manifolds, so we have to account there is a little difference for what the definition should be, and the appropriate one for hyperbolic manifolds with our notations and with our conventions is to have a -4 term here. Okay. So why is this? So why is Hawking mass interesting? Well, first off, it refers to another quantity known as the ADM mass. Instead, as follows: if we take a three-manifold that is asymptotically flat, meaning it's asymptotic to R3, the flat metric, and we start taking larger and larger spheres, then the Hawking mass is going to converge to the ADM mass of the three-manifold. And second of all, we have the result of Kerok that tells us that if we make our surface evolve by the inverse mean curvature flow, then the Hawking mass has to be non-decreasing. Where here, I'm assuming that the surface is both connected and the Deming space has no negative scalar curvature. And just for reference here, one interesting application once you have all these results in mind is the following theorem of using Immonen regarding the Riemannian Penrose inequality. It says the following: if we assume as before that M3 is asymptotically flat, it has non-negative scalar and has minimal boundary such that it's outermost. So I'm going to blur this concept for a little bit. Then it's going to say that the ADM mass is greater than or equal than the square root of the area of n divided by 16 pi when n is a connected component of the boundary. And more or less, and moreover, the result has says like it's going to be inequality if and only if m has the metric of a precise model. So a way to quickly summarize how this result goes is that well, we can more or less start inverse mean curvature flow. Well, it's not, after doing some work, but it's basically we start through mean curvature flow at the boundary and let it go further and further out on the manifold. And we study the Hawking mass along that flow. And all that the way that this inequality is going to be obtained is that the right-hand side is the initial state of the Hawking mass, whereas the left-hand side is the final state of Hawking. And because of the non-decreasing property, then we know that this equality has to follow. Okay. So let me now particularize and let me start trying to bring back a little bit the language of hyperbolic manifolds we saw before. So again, I'm going to have N3 to be a convex co-compact manifold. I'm going to have a region omega 0 that I'm going to denote by outermost. In the particular case, for me, what outermost is going to mean, or one of the properties that outermost I'm going to care mostly, is that any compact manifold immersed in M3 has to be inside this outermost region. Okay. Given that, I'm going to look now, I'm going to look at a very similar infimum as the one described for a superempty profile, but I'm not going to look to any possible domain omega. I'm going to look at domains omega that are going to contain my outermost region. So I'm looking at compact subset of M so that they contain omega 0. And moreover, I'm only going to take into account the volume that goes in between omega and omega 0. So here, for instance, in my example, omega could be this bigger tree manifold together with interior of this triple. Omega doesn't need to be necessarily connected. But all that it matters is that it contains this green region, and all this volume in between, once we add them up, it adds up to V. And then what the superempty profile is going to be the minimal perimeter of all the volumes containing RV for that given V. Okay. So what is going to be, what are some of the key properties we're going to be using? Well, first off is that for our setup, the profile has to be street increasing almost everywhere. And by this, I mean that the derivative has to be positive. And here, the way that we do it is as follows. I'm going to assume that that's not the case. I'm going to assume that my derivative is not decreasing, and because the profile is going to be differentiable almost everywhere, then I'm just going to assume that it's a usual derivative. Here, the important part to remember is that this derivative, if it exists in the traditional sense, only has to be equal to the mean curvature. So what this is going to mean is that we're going to have a surface whose mean curvature vector is pointing out strictly inwards. Now here, because I'm assuming that this boundary was outside the outermost region. Well, outside of the outermost region, I can basically use this region as a barrier, and this surface I'm assuming here by contradiction to create a minimal surface, a compact minimal surface outside of the outermost region, which is going to be a contradiction. So this picture above, this is not what the picture should look like. It should look like the picture below here. It should be a constant mean curvature surface with the mean curvature vector pointing upwards. Okay, so the derivative of the profile has to increase. And the reason why that is interesting is because of the following: is under now our corrected definition for the Hawking mass. So this again is the same definition here. All I'm using is that the evaluation of the profile is equal to the area. and the derivative of the profile is equal to the mean curvature. So this is it's just a rephrasing of the previous definition we have, is that this quantity is going to be monotone non-decreasing. And way to prove this is like, well, we can take the derivative of this expression and prove like this derivative has to be greater than or equal to 0. So that's from one side. From the other side, and then sort of like here, I try to compute two results in one, is going to be the following. It's like, well, moreover, more than being a monotone non-decreasing function, it's going to be a monotone non-decreasing non-positive function. And it has to be 0 if and only if the principal curvatures of the surface agree, of the surface realizing the particular V, which in particular is going to mean that my surface, that all the ends have to be functional. And again, this basically follows from the properties we had before. So we both know that the profile has to be extremely increasing, and the Hawking mass has to be monotone non-decreasing non-positive. Okay, so I'm going to pause here, and then I'm going to address the main result of my theorem with the end.